In physics, the dynamo theory proposes a mechanism by which a celestial body such as Earth or a star generates a magnetic field. The dynamo theory describes the process through which a rotating, convecting, and electrically conducting fluid can maintain a magnetic field over astronomical timescales. A dynamo is thought to be the source of the Earth's magnetic field, as well as the magnetic fields of other planets. History of theory. When William Gilbert published De Magneta in 1600, he concluded that the Earth is magnetic and proposed the first hypothesis for the origin of this magnetism, permanent magnetism such as that found in lodestone. In 1919, Joseph Larmor proposed that a dynamo might be generating the field. However, even after he advanced his hypothesis, some prominent scientists advanced alternate explanations. Einstein believed that there might be an asymmetry between the charges of the electron and proton so that the Earth's magnetic field would be produced by the entire Earth. The Nobel Prize winner Patrick Blackett did a series of experiments looking for a fundamental relation between angular momentum and magnetic moment, but found none. Walter M. Elsasser, considered a father of the presently accepted dynamo theory as an explanation of the Earth's magnetism, proposed that this magnetic field resulted from electric currents induced in the fluid outer core of the Earth. He revealed the history of the Earth's magnetic field through pioneering the study of the magnetic orientation of minerals in rocks. In order to maintain the magnetic field against ohmic decay, the outer core must be convecting. The convection is likely some combination of thermal and compositional convection. The mantle controls the rate at which heat is extracted from the core. Heat sources include gravitational energy released by the compression of the core, gravitational energy released by the rejection of light elements at the inner core boundary as it grows, latent heat of crystallization at the inner core boundary, and radioactivity of potassium, uranium and thorium. Initial models are focused on field generation by convection in the planet's fluid outer core. It was possible to show the generation of a strong, Earth-like field when the model assumed a uniform core surface temperature and exceptionally high viscosities for the core fluid. Computations which incorporated more realistic parameter values yielded magnetic fields that were less Earth-like, but also point the way to model refinements which may ultimately lead to an accurate analytic model. Slight variations in the core surface temperature, in the range of a few millikelvins, result in significant increases in convective flow and produce more realistic magnetic fields. Formal definition. Dynamo theory describes the process through which a rotating, convecting, and electrically conducting fluid acts to maintain a magnetic field. This theory is used to explain the presence of anomalously long-lived magnetic fields in astrophysical bodies. The conductive fluid in the geodynamo is liquid iron in the outer core, and in the solar dynamo is ionized gas at the tachocline. It was once believed that the dipole, which comprises much of the Earth's magnetic field and is misaligned along the rotation axis by 11.3 degrees, was caused by permanent magnetization of the materials in the Earth. This means that dynamo theory was originally used to explain the Sun's magnetic field in its relationship with that of the Earth. However, this hypothesis, which was initially proposed by Joseph Larmor in 1919, has been modified due to extensive studies of magnetic secular variation, paleomagnetism, seismology, and the solar system's abundance of elements. Also, the application of the theories of Carl Friedrich Gauss to magnetic observations showed that Earth's magnetic field had an internal, rather than external, origin. There are three requisites for a dynamo to operate: an electrically conductive fluid medium, kinetic energy provided by planetary rotation, an internal energy source to drive convective motions within the fluid. In the case of the Earth, the magnetic field is induced and constantly maintained by the convection of liquid iron in the outer core. A requirement for the induction of field is a rotating fluid. Rotation in the outer core is supplied by the Coriolis effect caused by the rotation of the Earth. The Coriolis force tends to organize fluid motions and electric currents into columns aligned with the rotation axis. Induction or creation of magnetic field is described by the induction equation, where U is velocity, B is magnetic field, T is time, and is the magnetic diffusivity with electrical conductivity and permeability. The ratio of the second term on the right-hand side to the first term gives the magnetic Reynolds number, a dimensionless ratio of advection of magnetic field to diffusion. Tidal heating supporting a dynamo. Tidal forces between celestial orbiting bodies cause friction that heats up to their interiors. This is known as tidal heating, and it helps keep the interior liquid. A liquid interior that can conduct electricity is required to produce a dynamo. Saturn's Enceladus and Jupiter's Io have enough tidal heating to liquefy their inner cores, but they may not create a dynamo because they cannot conduct electricity. Mercury, despite its small size, has a magnetic field, because it has a conductive liquid core created by its ion composition and friction resulting from its highly elliptical orbit. It is theorized that the Moon once had a magnetic field, based on evidence from magnetized lunar rocks, due to its short-lived closer distance to Earth creating tidal heating. An orbit and rotation of a planet helps provide a liquid core, and supplements kinetic energy that supports a dynamo action. Kinematic dynamo theory. In kinematic dynamo theory, the velocity field is prescribed, instead of being a dynamic variable. This method cannot provide the time variable behavior of a fully nonlinear chaotic dynamo but is useful in studying how magnetic field strength varies with the flow structure and speed, using Maxwell's equations simultaneously with the curl of Ohm's law. One can derive what is basically the linear eigenvalue equation for magnetic fields, which can be done when assuming that the magnetic field is independent from the velocity field. One arrives at a critical magnetic Reynolds number above which the flow strength is sufficient to amplify the imposed magnetic field, and below which it decays. By applying a certain velocity field to a small magnetic field, it can be determined through observation whether the magnetic field tends to grow or not in reaction to the applied flow. If the magnetic field does grow, then the system is either capable of dynamo action or is a dynamo, but if the magnetic field does not grow, then it is simply referred to as non-dynamo. The membrane paradigm is a way of looking at black holes that allows for the material near their surfaces to be expressed in the language of dynamo theory. Nonlinear dynamo theory. The kinematic approximation becomes invalid when the magnetic field becomes strong enough to affect the fluid motions. In that case, the velocity field becomes affected by the Lorentz force, and so the induction equation is no longer linear in the magnetic field. In most cases, this leads to a quenching of the amplitude of the dynamo. Such dynamos are sometimes also referred to as hydromagnetic dynamos. Virtually all dynamos in astrophysics and geophysics are hydromagnetic dynamos. Numerical models are used to simulate fully nonlinear dynamos. A minimum of 5 equations are needed. They are as follows. The induction equation, see above. Maxwell's equation. The Boussinesq approximation is often used, in which the continuity equation for conservation of masses and the Navier-Stokes equation for conservation of momentum is, whereas the kinematic viscosity is the density perturbation that provides buoyancy, is the rotation rate of the Earth, and is the electric current density. Finally, a transport equation, usually of heat, where T is temperature, is the thermal diffusivity with K thermal conductivity, heat capacity, and density, and as an optional heat source. Often the pressure is the dynamic pressure, with the hydrostatic pressure and centripetal potential removed. These equations are then non-dimensionalized, introducing the non-dimensional parameters, where R is the Rayleigh number, E the Ekman number, PR and PM, the Prandtl and magnetic Prandtl number. Magnetic field scaling is often in Elsasser number units. Numerical models. The equations for the geodynamo are enormously difficult to solve, and the realism of the solutions is limited mainly by computer power. For decades, theorists were confined to kinematic dynamo models described above, in which the fluid motion is chosen in advance and the effect on the magnetic field calculated. Kinematic dynamo theory was mainly a matter of trying different flow geometries and seeing whether they could sustain a dynamo. The first self-consistent dynamo models, ones that determine both the fluid motions and the magnetic field, were developed by two groups in 1995, one in Japan and one in the United States. The latter received significant attention because it successfully reproduced some of the characteristics of the Earth's field, including geomagnetic reversals.